Okay, so we're very happy to have Kevin Kelly from Texas A&M to tell us about some new thoughts on and old anomalies.
Oh, should be an old anomaly. Can't write anymore. So, hi, thanks for having me. It's been a real treat visiting here for the last few days. I'm going to tell a story about this long-standing anomaly from the MiniBooNE neutrino experiment. Some new data that maybe isn't super consistent with it, as well as some deep dive into their background. So it's going to get a little statistical for a few minutes in there. Just trying to really scrutinize these results from every angle before we jump to BSM, as much as many of us want it to be BSM. So I'll briefly, zoom in some. There's a question in the chat,
Yeah, I'll do that.
Okay. I'll briefly highlight how we got to this point, where some of these anomalies came from, and how there was motivation for the potential of new neutrino states to exist beyond the 3 in the standard model. I'll talk about recent results, so post MiniBooNE, and how we can interpret those in a full 4 neutrino framework to see whether or not they're consistent. And then I'll go beyond the sterile neutrino picture. So whether or not these are pointing to some more exotic new physics, some exotic signatures that we can test in some currently operating or soon to be operating experiments, as well as, like I said, going deep into some of these background studies. So over the course of the last 30 years or so, we learned a lot about neutrinos. Unexpectedly, they have mass. However, that mass is very small. So based on oscillation experiments, we can determine that there are 2 non-zero mass squared splittings between the 3 different light neutrino states, on the order of 10⁻³ and 10⁻⁴ in these units of electron volt squared. Interestingly, from oscillations, we don't know whether they follow this normal ordering, 1, 2, 3, or the inverted ordering, 3, 1, 2. Yeah, the jury's still out on measuring that. And then we also know from, mostly from cosmology, the lack of observations of contribution of neutrino masses to large scale structure, damping, that the neutrino masses can't be too heavy. Some of the neutrino masses can't be bigger than something like 0.1, 0.2 electron volts. So these two facts combined, the fact that there is some non-zero gap between the states, but a maximum of the sum of the masses, around 0.1 eV, means that neutrinos have to have really, really small masses, much smaller than the other fermions. So just a quick.
The latest, was somebody claiming that like normal was preferred over inverted a little bit, or?
Yeah, there's claims at the level of like 2 to 3 sigma that normal is preferred over inverted. So it's modest evidence, I guess. If you combine the oscillation results with cosmology, because the inverted ordering wants there to be a larger sum in the neutrino masses just based on that stratification. If you try to combine the cosmological data with the oscillation data, you end up with a bigger preference for the normal ordering, but that depends on the type of prior you take on the sum of masses. So I would rather wait for more oscillation data that can uncover this before I say one way or another. So where do we actually measure these oscillations on Earth? Well, typically, if you calculate what a neutrino oscillation looks like in vacuum, then a transition probability depends on this sine squared term, delta m squared L over 4e. And so you can ask, where is this sine squared term maximized? And depending on which mass squared splitting you're talking about, those 2 different sub EV squared numbers, you'll have maximal oscillations along these different dashed lines. And as you can see, there are labels of experiments on there that are either currently operating or plan to be operating. They're designed specifically to measure these mass squared splittings, measure the associated coefficients of these sine squared terms, do precision measurements of these things. However, what I'm hiding is a lie, and that is that there have been many experiments populating a different phantom diagonal line in this same L over E space. Some names you may be familiar with, like MiniBooNE and LSND from the early 2000s, that seem to follow a line corresponding to a new delta m squared that's a factor of maybe 100 to 1,000 bigger than those existing ones. So let me briefly rewind to what happened with LSND and MiniBooNE. Well, LSND was designed to look for neutrino events in the LS&D detector, starting from a relatively low energy proton beam, effectively hitting a copper beam stop and having pion decay at rest, producing a source of neutrinos. So producing muon neutrinos, electron neutrinos, and electron or muon type antineutrinos. Notably, in the pi plus decay at rest chain, you do not create any sizable contribution of Nui bars. Their detector was designed specifically to look for Nui bars, so look for an electron produced or a positron produced in Nui bar inverse beta decay capture, as well as the associated neutron that's kicked out. And they saw a significant excess. So a significant excess above background indicated by the blue hatched region. And if you say that this is coming from some new oscillation, maybe it's just constant with respect to energy, that oscillation probability works out to about a few times 10 to the minus 3. Nui bars oscillating into Nui bars. You can see the statistical significance is about 4 sigma from LS&D. So MiniBooNE came along to try to test this anomaly. Specifically, it was designed to test this anomaly in a similar range of L divided by E, so a similar diagonal in that L versus E plot, but very different L and very different E, hoping to eliminate some of the systematics maybe associated with neutrino production, these scattering cross sections, you name it. So it was designed to operate as a pion decay and flight beam, which is what most conventional neutrino beams use now. And it could operate either in neutrino mode or anti-neutrino mode based on the focusing of its magnetic horns. And again, what they see is a significant excess above background, looking for nu mu oscillating into nu e, or nu mu bar oscillating into nu e bar. So this filled histogram shows their expected background, and the black dots indicate their data. And there's a clear excess, especially at low energies. So they claim to see both neutrino anomalous appearance and anti-neutrino anomalous appearance. So if you ask, okay, how does this data from MiniBooNE look as a function of that L divided by E, and how does the data from LS&D look in that same space? You see that they all seem to be following this general upsweep that would be indicated by that sine squared delta m squared L over E term. So they're vaguely consistent if you look at it in this space. And you can do a fit. This is a simple 2 neutrino fit where you say that there's muons oscillating into electrons, muon neutrinos oscillating into electron neutrinos, not worried too much about the light mass squared splittings. And you can see that the results are generally consistent as a function of this effective mixing angle, sine squared 2 theta, and this new mass squared splitting. So LS&D are the blue regions, and then MiniBooNE are the different colored contours. And we can see that at 1 sigma, they're pretty consistent. They tend to want this large mixing, low mass squared splitting, which might not be as, viable. There's plenty of support in these 2 distributions, pointing towards a new state around an electron volt in mass. We also know, though, from measurements of the Z boson, especially at LEP, that measurements of the invisible width of the Z boson indicate that there's only 3 species of neutrinos that the weak force can decay into. So if you're going to add any light neutral fermion state at the EV scale, it better be sterile, meaning that it better not interact with the standard model weak interactions. So putting together all that we've seen so far, I said that cosmology tells us that we want the neutrino masses to be no bigger than order electron volt, even maybe 0.1 EV, maybe even order of magnitude here. But oscillations tell us that at least 2 of them have to be heavier than about 10 to the minus 2 electron volts. But there's this chasm between the standard model charged fermion masses and these neutrino masses. So from a model building perspective, it's not too unappealing to consider adding new fermion states. The canonical way to do this is by adding a Higgs-like interaction, a Yukawa interaction between the standard model neutrinos in the charged lepton doublet with these new states. And then you can also, because this new state is a gauge singlet, you can give it its own Majorana mass. And depending on the relative mass scales of this Majorana mass and that Yukawa coupling times the Higgs VEV, then you can open up what's known as the seesaw mechanism, where you end up with 2 states, one roughly at the Majorana mass of this singlet, and one at this suppressed mass scale that goes like y times v squared divided by that mass. So depending on how big this Yukawa coupling is, depending on how big you have mixing between maybe a 3+3 mixing matrix, you can align things such that heavier singlet states produce neutrinos with suppressed masses that are mostly standard model-like, explaining this chasm that we see. Now, maybe this is harder to do if you take that singlet state down to EV scales, but nevertheless, maybe with a bit of fine-tuning, it might work, and then you have some additional partners at heavier masses. So this is your canonical seesaw mechanism. I can't go by without putting this slide in. Why else might you care about sterile neutrinos at these, I don't know, EV to keV mass scales? Well, there have been hints over time, possibly for 7 keV sterile neutrinos acting as dark matter, decaying throughout the local group. We can debate whether those are strong signals or not. And then there's been work in previous years about how you would be able to produce that dark matter in either the universe, the sterile neutrino dark matter, maybe via some additional interactions between the standard model neutrinos or the sterile neutrinos themselves. There's also this Hubble tension that we were talking about over lunch. People have talked about self-interacting neutrino species delaying free streaming in the early universe that can help ameliorate that tension. So possibly additional sterile neutrino species, additional self-interactions could do that for you. So light mediators, light neutrinos may freak you out for cosmology. I think there's plenty of interesting physics to be done at those low mass scales.
What's the latest on this 8.5 kV line?
Yeah, so there have been these hints over time, maybe over the last 10 years or so, but then over the last 3-4 years, I think more evidence has come out that's inconsistent with that interpretation.
Sorry, that question was inaudible. Could you repeat it?
Slightly the exome stuff. And yeah, according to at least more recent analyses, it's more or less gone. But I mean, we're the people that did it, so.
But what is going on? The line, I think, was pretty robustly there, but it wasn't really...
Excuse me, can somebody do something about the audio? The audio pickup of the audience is terrible.
Line data, and they found that by changing the systematics, like the window of the energy window that they're fitting to, that could actually also make it go away, even in some of these original data sets. So, I mean,
I think there are answers to that. I think that, you know, it doesn't look great.
Yeah, it doesn't look great.
But I bet if you talk to some of the original people, they would not tell, they would say that it's still an open question.
I'll qualify it as murky at best.
Yes.
You know, wait for the data, is what I will say.
Yeah.
Wait for the data.
Yeah. Okay, so there are consequences, obviously, in invoking new light species. The first off is that this effective 2-flavor mixing that I was showing, these results of MiniBooNE and LSMD with respect to, well, it depends on the model. If you say that there's a 4th neutrino, not just this effective 2-flavor mixing, then this requires extending our 3x3 mixing matrix to a 4x4 one. So we can actually ask, what is that effective mixing angle? And it depends on this product of new elements in that 4x4 mixing matrix that would be 0 in the standard model case. So in order for this mixing angle, the effective one, to be non-zero, then these 2 new ones have to both be non-zero. And each of them being non-zero drives new phenomena. Specifically, if this first one, this electron mixing, is non-zero, then there has to be anomalous electron-neutrino disappearance at the same L/E where MiniBooNE and LSMD are seeing appearance. And likewise, if there's non-zero muon mixing, there should be anomalous muon-neutrino disappearance at the same L/E. So the nice thing about this 3+1 model is that if there is anomalous appearance, then we can check it for anomalous disappearance of electrons and muon neutrinos at the same baseline divided by energy and stress test this model. So let me first give the rapid update to what's been going on with searches for electron neutrino disappearance at the same L/E. Well, the best way to do that is measurements of reactor antineutrinos. So either research reactors or actual commercial nuclear reactors produce a whole lot of electron type antineutrinos, and people have gotten smart about building detectors that can go very close to them. So these are lower energy than MiniBooNE, but much closer distances for the same L over E. So they're looking for anomalous disappearance of electron-type antineutrinos between the source and the detector. And the key challenge in these types of experiments is that there's a lot of uncertainty on the flux produced by the source. In terms of the overall rate or as a function of energy, these are hard calculations to do. And so there's a decent theoretical uncertainty on that flux prediction. And so people have gotten around that with clever ideas about how to avoid those types of uncertainties, specifically by performing multi-distance measurements, either with a detector that can move or a detector that's segmented in its geometry, or even in some cases, a nuclear reactor source that's movable, the one that's kind of bonkers to me. You can eliminate a lot of those uncertainties in that way by performing these multi-detector or multi-distance fits and see whether the flux follows this 1 over L squared dependence you would expect from an isotropic source, or if there's wiggles on top of that corresponding to anomalous neutrino disappearance. The answer is that at least at 2 sigma confidence, there is no anomalous electron antineutrino disappearance at the same delta M squared scales that LSND and MiniBooNE are seeing appearance. So this is a paper from late 2021. They see some hints at 1 sigma, these kind of harmonic islands going up in L over E or mass squared splitting space. But again, at 2 sigma, this combination of these 5 different experiments does not see any hints at high confidence. At the same time, you can look for muon neutrino disappearance. First, you can do that in one of these conventional beam type experiments that makes a lot of new mu's. This was the MINOS and MINOS Plus collaboration at Fermilab that put out their final results in early 2020. And again, they don't see any deviation from what they expect. And they can set constraints in this parameter space that are very strong in terms of this UE or U mu 4 squared mixing angle. Again, covering the same range of delta M squared that MiniBooNE and LSND. IceCube, the neutrino observatory at the South Pole, also measures a whole ton of muon neutrinos, mostly produced in the atmosphere. The physics of how the sterile neutrino affects the oscillations in IceCube is a little bit more subtle because it actually has to do with the fact that muon neutrinos can interact with the Earth's matter while they travel through, the entire Earth diameter of this material. And the sterile enters this whole problem in an interesting way because it doesn't interact with the matter. Nevertheless, they set this constraint at 99% confidence level. They do see this hint that might be tantalizing around 2 electron volts squared, but it's a 90% confidence hint. I think it's less than 2 sigma. So again, it's modest at best. So if you take 3 sigma as your threshold, then neither of these channels see any positive hint, nor does electron neutrino disappearance. Yeah.
With such large mixing angles and low masses, how are these not ruled out by ineffective?
Good. The question was, it's such large mixing angle and low masses, how is this not ruled out by ineffective? It's not. I think it's just that the production rate in the early universe scales with the mass. And so if you go to these very light masses, you just don't have enough time to thermalize it before BBN or before CMB. I'll get to that in just a second, actually, a more precise statement about the cosmology. Yeah. I think I was thinking about the Yukawa interactions, but let's talk about the mixing in just a second. Okay. So groups of people have analyzed all of these pieces of evidence for LSND, MiniBooNE, null results, etc. Summarized in many papers circa 2019, showing that the hints for appearance, that if you combine all hints for appearance in these fits, you prefer to be in these red regions, red and pink. But if you look at all the disappearance measurements, then you can constrain everything to the right of these blue lines. And so there's an inconsistency between hints for appearance and null results for disappearance. You can also ask where's the best fit in these parameter spaces. You can get a relatively small constrained region. However, because of this tension between the 2 data sets, it's not a very good fit. Okay, so yeah, actually going back to your previous question, yes, the answer is you will thermalize if, this is looking at if it's coupling just to electron flavor. You will thermalize it significantly in the early universe for substantially large mixing, but the boundary might not be as harsh as you'd expect. So the best fit regions are definitely in tension with cosmology, so this would predict an ineffective around the time of BBN on the order of 3.7, 3.8. So if you were to say that this thing really does exist, you probably have to do additional model building to explain why this is suppressed in your universe. Does that answer your question?
Yeah.
Okay. So even if these data sets were consistent, you'd still have more work to do with cosmology. Okay, so as of 2019, feels like a long time ago now. My thoughts were, let's wait for the data. At the time, I knew that there were more experiments coming online that would test this. I figured I could be patient. I could afford to be patient. What's going to happen in the next 4 years that could, I don't know, derail the entire society? Let's be patient. Okay, so over that time span from 2019 till now, more data came out, specifically from the MicroBooNE experiment. So mini, micro, I know it's a bad naming convention. Micro is newer than mini, but maybe smaller. Yeah. So one big challenge for MiniBooNE is its detection technique. So MiniBooNE was designed to mostly look for Cherenkov radiation in its liquid simulator volume. And Cherenkov radiation for neutrino experiments is notoriously bad at discriminating electrons from photons from two photon pairs. All of those look vaguely the same, especially at these low few hundred MeV energies for a detector like MiniBooNE. And so if you look at the types of backgrounds that are contributing to MiniBooNE's expected background budget, it's things like misidentified pi naughts that decay into two photon pairs, or a delta resonance produced in neutrino scattering that decays into a nucleon and a photon. These photons are indistinguishable from electrons to them. And so there was a proposal to build a suite of detectors at Fermilab to kind of test this once and for all. First off, there would be 3 detectors, what's called SBND, MicroBooNE, and Icarus. But they would also use this liquid argon time projection chamber technology that is way, way better at particle identification, way better at energy resolution than previous detector technologies. And so you can tell the difference between an electron that starts to shower right as it's produced versus a photon, for instance, which has some travel distance before pair converting into an electron-positron pair in these detectors. And so the plan was to build these 3 detectors, measure neutrino oscillations, and if they have a null result, they would be able to rule out the preferred region by LSND and MiniBooNE at very high confidence. So MicroBooNE started releasing their first results in late 2021. The first thing that they did was they looked for photons. People have been saying for a while, well, you know, that delta to N gamma background in MiniBooNE, we don't really know that branching ratio or the production rate of these deltas in these experiments. So what if that's significantly higher than what the standard model predicts, or just these simple models? MicroBooNE went and they looked for photons coming from delta resonance decays and did not find any excess. So they were able to disfavor that explanation of the MiniBooNE anomaly at nearly 2 sigma confidence. So this is a single photon model, but it's a specific single photon explanation for MiniBooNE. Then a couple months later, they came out with a whole slew of analyses looking for single electron neutrino events. So the standard nu-mu to nu-e analysis. And what they did was they did this template-based model where they said, okay, let's assume that everything in MiniBooNE, data minus background, is our signal. And let's inject that signal, let's do some unfolding, inject that signal into MicroBooNE and ask, what should we see? And if we see it, great. If not, we can exclude that expected template times some scaling parameter and ask how well we can exclude that scaling parameter equals 1 at high confidence. So they have a whole number of channels of different selections. For instance, this left one is just looking for a single electron plus anything in their data. And then these other ones are more fine-tuned selections that have lower efficiency but much lower backgrounds. And we shouldn't take these different measurements in tandem because they are not statistically separate, but all of them, except for maybe this one channel that has low significance, disfavor this template model at roughly 2 sigma. So these first results from late 2021 seem to be inconsistent with this excess explanation of nu-mu's oscillating to nu-e's in MiniBooNE. Now, I'll skip over this because all I want to say here is that these different channels that they produced are actually nicely complementary, because this inclusive channel, while it has a lot of background, that background can actually be useful. All of this green background that they expect to see in MicroBooNE is from electron neutrinos that were produced in the beam that in a full 4-flavor model could be oscillating themselves. Whereas this CCQE channel has high purity, low backgrounds, and so there's an interplay between these two that can be exploited. So my collaborators and I came in and we asked, how can we interpret these data in the context of one of these simple two flavor scenarios? And what we showed is that MicroBooNE can set constraints at the 3 sigma level shown by these blue and orange lines using 2 of these different data sets. And so it was able, MicroBooNE with this preliminary data was able to exclude a whole swath of parameter space with this inclusive channel that rolls out a good chunk of what was favored by MiniBooNE in the first place. However, there's still plenty of parameter space, for instance, down here, up here, that is consistent with both experiments at high confidence. So while they started to rule out this parameter space, there's still a lot of work to be done. There was a lot of trumpeting when that first result came out about the death of the sterile neutrino, but I think this kind of proves that there's still a little bit more to be done. And that full SBN suite of detectors will really be able to do this measurement. We did some comparisons against Asimov expectations. Looks like they got a little bit lucky with statistical fluctuations of their data, but not outside of what was expected. But then we also opened it up to this complete 4-neutrino framework. So if there is anomalous nu mu to nu e appearance, there has to be anomalous nu mu and nu e disappearance. And their data are rich in those expected nu mu and nu e backgrounds. So for instance, this data set that I showed you before, this green background is all expected nu e. And if you have anomalous oscillations happening, then there should be anomalous oscillations on top of that green background as well. And in this muon sample that has way, way larger statistics than the nu e sample. And so we put this all to work and did an analysis in this 4-flavor case. And what we found is that while they're able to constrain this just pure electron neutrino disappearance, they're not competitive with, for instance, those electron antineutrino results from nuclear reactors, which is what was expected, frankly. So it's nice to see that they can do this, but again, these reactors are setting a 3 sigma constraint that's blowing them out of the water, because that's what they're built to do. In terms of looking for muon neutrino disappearance, on the other hand, it's actually quite interesting. I mentioned that hint from IceCube at 90% confidence earlier. And what we were able to show is that actually MicroBooNE is able to start constraining that explanation of anomalous signals in IceCube. So they are playing a role in this whole 4-dimensional parameter space as well. So this is looking at appearance in that 2-flavor model. We also asked what happens in that full 4-flavor model. It gets a little bit dicey because there's an additional parameter to marginalize over. So these contours move in unexpected ways. But all of this is to say that there's still plenty of viable parameter space that MicroBooNE has yet to explore, but hopefully will over time, especially with these newer experiments coming online. And then just in the last couple of months, MicroBooNE started putting out their own analyses in this type of way as well. And we humble theorists were really excited to see just how well we could do with our simple tool. So this is that full 4-flavor model. We think we did a pretty good job. This is that simple 2-flavor model. We think we understand why they got a little bit better sensitivity at high delta M squared than we did, but all this is to say we think we did a pretty spot on job for, again, a group of a handful of theorists not working with that data. And then they also did this analysis looking for electron neutrino disappearance, and again, we think we did a pretty dang good job. Again, unfortunately, it's not as competitive with other probes for this type of physics. Okay, so I'm going to put that aside and talk about going beyond these sterile neutrino hypotheses, because I think that's where the real magic is. I would love it if this were actually new physics beyond that explanation. And so what else could it be? Well, first off, it could be other sources of electron neutrinos in a beam like MiniBooNE. They were looking purely for oscillations, nu mu to nu e, but there are plenty of model scenarios that ask, okay, what else could produce an anomalous set of nu e's in this data? I was part of an effort that during Snowmass to kind of tabulate all of these, kind of even give scores to different models corresponding to different data sets. It was a lot of work, but there are some models that seem to do okay, that still evade constraints from things like MicroBooNE, that will be tested over time. So some of these are pure sources of electron neutrinos, and other are more interesting sources of more exotic signals. So for instance, I mentioned that a detector like MiniBooNE could not tell the difference between a single electron or a single photon. Other signals that it wouldn't be able to discriminate against that are pairs of electrons and positrons that are either highly overlapping, so small opening angle, or highly asymmetric in terms of their energies. This would look like one shower to them, more or less.
This table is terrifying. There's no masses. What's the difference between a green check and an orange check?
A green check and an orange check. I think a green check is like all is good, and an orange check is like, it's okay. Yeah. I mean, any sort of score you try to give to this thing is going to be subjective, right? And it's going to be biased because I'm sure these references have overlap with the author list of this white paper. So it's definitely not an unbiased process.
Sorry, I'm confused about the sign of the checks.
So just to give you a flavor for what could be happening, there's some explanations where, for instance, you have a sterile neutrino that's actually way heavier, that's like keV scale, that's impacting these oscillations and then decaying into some new very light scalar, we call phi, along with neutrinos that are electron flavor. So you have nu mu's oscillating into sterile neutrinos that then decay, and then you produce extra antineutrinos. Glennis, I see your question in the chat. Yes, the check marks means that it is consistent with the data.
Just because
Sorry, consistent with explaining.
Great question, yeah.
Wait.
So the answer, let's just ignore this. It does a good fit to MiniBooNE, great. The answer to your question, Josh, about cosmology is that you can basically do well with 2 out of 3 of any of these 3 options. Solve MiniBooNE, solve LSND, and be consistent with cosmology. You can solve LSND and MiniBooNE roughly in this region, but cosmology says that you want to be up here. You can solve cosmology and MiniBooNE if you're up here, but then you're inconsistent with LSND, and so on. So it does a decent job at 2 out of 3. If you could somehow delay, it's all about adding additional, so many interactions that you delay free streaming. If you can somehow work around that, then you might be in business. Let's get past this in the interest of time and go on to this. So I've been saying that MiniBooNE has a hard time of telling different signals apart from another. The main one being single electrons from single photons from photon pairs. And there's a huge source of background expected in MiniBooNE from photon pairs, and that is neutrino scatters, neutral current, kicks off a pi naught. Pi naught decays into 2 photons, and that's all you see in the event. Those pions at low energy can make low energy photons that are really hard to reconstruct, and especially if those photon pairs are overlapping or highly asymmetric, or one leaves the detector before it converts into an E+ E- pair. All of these effects can lead to signatures that look like single electron showers in MiniBooNE. So we wanted to ask, how do they actually deal with this in their data? And this is where we're going to get into the weeds of statistics for just a little bit, so bear with me. MiniBooNE provided us with their expected background rate of these neutral current pi naught events as a function of basically the 2 photon energy. And so we wanted to come up with a phenomenologist's way of reconstructing this. What specifically is it about these 2 photon pairs in terms of their energy asymmetry, their opening angle, about the kinematics that leads to this general upturn, and how robust is this prediction as you say change your assumptions about neutrino scattering in your detector? And so the kinematical variables that we keyed in on that we think are relevant are the opening angle. Bigger opening angle is easier to veto. Smaller opening angle will look more like their signal. And then this asymmetry. So the maximum energy of photons in the event divided by the total energy. If that's closer to 1, this will look more like a single shower event. If it's smaller, it's closer to a half, it will look more like a 2 photon system that you can reconstruct. So let's pick one of these bins, around 200 MeV or so, and ask what events from one of these neutrino event generators, the one that MiniBooNE used, look like in that energy range. So we did that. So this is from showers with between 220 and 240 MeV in that photon energy. We asked, okay, let's run this through our simulation of how photons behave in MiniBooNE and ask what is their opening angle on the x-axis versus this energy asymmetry on the y-axis. And so from our logic, the events that are towards the bottom left of this space are going to look less like a single shower. They're easier to veto. And the events towards the top right are going to be the ones that look more like a single shower, more like their expected electron neutrino signal. Those are the problem. You actually notice that there's a dot up in that corner. Those are events where the pion decayed into two photons and one of them escaped the detector before converting. If you only have one photon, it's going to look like a single electromagnetic shower. So what we did was we developed a different sets of shapes in this space, trying to separate two shower-like events from single shower-like ones. So different shapes, different circles centered on different points in this parameter space, or just a pure diagonal cut, and designed a set of cuts as a function of visible energy in these visible space that allowed us to perfectly match their expected background. Because we don't have access to their actual likelihood model that separates electrons from photons, electrons from pions. And so this was the best that we could do. We could come up with a set of assumptions that by fiat matches what they expect. So we can ask, okay, let's look at the distributions of events that survive these cuts after we run it through our analysis pipeline. So the key one that we thought we would look at was this. They provided figures like this in their most recent analysis, where they took their events and binned them in terms of the visible energy, so like those two photon showers, and asked, okay, of the events that look electron-like, these are the problematic ones, what is the direction of that predominant shower? If I said that this really was an electron, what direction is that electron going? And this variable matters for then determining the inferred neutrino energy that they do all of their analyses with respect to. So what we found when we designed our set of cuts and we ran them through this pipeline, again, by definition, we're going to match the total rate in any one of these bins by definition because we constructed our cuts in that way. But the fact that we get pretty good agreement in these shapes, our green histograms versus their red ones, was not trivial. And so the fact that we were able to do that, we were pretty proud of it. And so if you have good agreement in the shape in any one of these bins and in the overall rate in each bin, you're going to agree very well in terms of this variable, the quasi-elastic neutrino energy, which again is the variable that they use for their analyses. Yeah?
I was wondering about, is this just the tail end of the peak?
The tail end of which peak?
Of the peak for the event, so the event occurring in, or like the energy peak of that.
This is going from 100 MeV visible energy up to 460, which is going, it's most of this distribution. So it's most of that expected background. Is that your question?
I guess because I was just trying to understand if what we're doing is trying to measure if the peak is wider than it was meant to be, to show that there's extra information or like extra.
Yeah, effectively, that's what we're getting at. These events, so this is visible energy, these correspond in terms of what MiniBooNE measured. So again, all of their analyses are done with respect to this quantity, this reconstructed quasi-elastic neutrino energy. And so it corresponds to kind of these first several bins of this red histogram. And we're trying to ask whether that red histogram should be bigger or not. Yeah. Okay, so we did this analysis. We got these spectra that seem to match pretty well in shape. However, and pretty well in overall rate. So we were able to match their E nu QE background pretty well. However, the thing that we noticed when we started making these figures was just how smooth our distributions were compared to theirs. So if you look at this second plot, for instance, you see that there's a lot of bin-to-bin jitter around our expected prediction, on the order of 5 to 10s of events in each of these bins, and this will start to add up if you start to add all these bins together to get a predicted event rate. And so what we did was we took our simulation and we compared it against the number of Monte Carlo events that they actually used in their background studies, which was comparable to the number of events expected in their experiment. So we took ours and we divided it up into subsamples that were the same size as theirs in terms of the actual Monte Carlo data that we're analyzing. And when we took ours and we divided it up into those 100 subsamples, each comparable in Monte Carlo size, and asked how does our prediction change as a function of those different subsamples, we found that we got a really big spread in terms of these event rates in these bins, purely from Monte Carlo statistics. You run this neutrino event generator, you decay these pions into photons, you ask how do those photons look in your detector. And what we find is that overall you can expect shifts that are relatively large as a function of these important parameters in your detector. Again, these are Monte Carlo samples that are consistent in size with what MiniBooNE does in their analysis. So we can ask, okay, how many events of this type do we expect in the background, including this effect from Monte Carlo statistical uncertainty? And we get an answer that has a median and a mean close to what they predict. However, this spread in uncertainty, if it's two-sided, is on the order of 300 events. So let's say a one-sided uncertainty on the order of 150 events, where they claim that this prediction, this event rate, is like 730 plus or minus 20. And so we're getting an uncertainty on this prediction that is significantly higher than theirs, and it would be a significant contribution to their uncertainty budget if this effect is present.
Right, where is that coming from? Because the fractional error bar seemed kind of small on the previous plot.
Yeah, good. So this is the fractional error bar shown. They're all correlated, is the short answer.
So you're doing something more sophisticated than just Poisson statistics in each bin?
Yeah, so what's shown here, let's pick a bin. What the range that's shown is the expected plus or minus 2 sigma range possible in our 100 iterations of this.
Right, so let's say in the bin you were just pointing at, right?
Yep.
So you have 10 events, so naturally from Poisson statistics I expect, plus or minus 3. Yeah.
Sure.
But is that what you're doing to get these error bars, or is there some additional randomness in the...
Good. So these are just derived by running that pipeline 100 times and asking what comes out. And so if everything is Gaussian, you would expect, or Poissonian, you would expect.
I guess I'm asking, what are the correlations there?
They're decent. I've started looking into this more recently because we're doing battle with the referee. And the answer is, bin to bin, these are correlated at maybe the 30% level. Enough that when you integrate over one of these slices or integrate over this whole distribution, you can get effects that contribute to much higher than root n.
Is that their defense if you talk to them that it's highly correlated?
That's our defense.
What's your defense?
They say it's not correlated and we see root n. But we don't think that they've done an apples to apples comparison with what we've done here.
Why would they be correlated?
Great question. If you run a neutrino event generator and you take out all the events that have a certain energy range, like this, and you ask, how are my events distributed in terms of opening angle versus asymmetry? What we have found so far, and again, we're still digging into this because it's a little too complicated, is that if you run one iteration of this, and then you run another iteration of this, same Monte Carlo generator, and you just decay those pions, this distribution can kind of walk in different directions.
You mean it's the same pions each time?
Yep, but the uncertainty on energy is pretty bad, or sorry, the photons energies is pretty bad down at these like 50 MeV, 20 MeV energies. And so again, what we're finding is that it's mostly because of re-decaying those pions into photons and accounting for these detector effects lead to kind of these distributions walking around. And so if you place a cut here, then you kind of see a whole shift of events up or down together as you do different Monte Carlo iterations. Yeah. I'm confident we're doing it right, but MiniBooNE isn't, and we're trying to get to the bottom of it. Does that answer your question?
Yeah, I think the answer is they're reusing the pions and then just decaying them differently.
That's what we're doing.
That's what you're doing.
They only ever
They only did
produced
it
one
once.
sample that was comparable to their data size and estimated
Right.
what
But then
fractions.
they're
were.
assuming Poisson statistics, whereas it's not.
We see that it's not. They are confident that it is, but again, we're still debating.
So shouldn't this distribution just converge to something like, say you have enough samples to actually get the true distribution?
It should, but unless you demonstrate that you're in that large statistics limit, how do you know that you are?
Statistics are just too low.
Yeah.
Like, okay.
Yeah, the neutrino event generators themselves are relatively complex beasts, and so I wouldn't be surprised if you have to run them a while before you actually hit that limit. We don't think we're in that limit for events samples of this size. Okay, so we tried to correct for this effect, so to speak. So instead of deriving one set of cuts that will match their expected distributions, we tried to ask, okay, let's take those noisy samples and come up with a set of cuts on those different noisy samples that each reproduce their samples, and then apply those different sets of cuts to the big sample that hopefully is already in the large statistics limit. This is 100 times their Monte Carlo statistics. So what you find is that if you analyze the individual noisy samples, you get a spread in distributions of cuts that would produce the same event rate in this bin for these different noisy samples. Oh, I see Clemens is asking a question. Yeah.
It seems the volume seems to be off. Can you turn on the volume?
Yeah, somehow she said her laptop audio has problem. There's a sound in the room on. There's nothing on the room at all. So she can hear us.
Could you try now, Glennis?
Can you hear me now?
Yes.
Okay, thank you. What I'm having trouble understanding is it that they won't tell you what their cuts are? It sounds like you're trying to reverse engineer what they've done. That's egregious. How can they be complaining about your paper if they won't tell you what their cut system was?
Right. So their cut is on they define as a function of all of their detector information, like their PMT responses. They define an electron pion likelihood, and they cut on that quantity. And so this is our best chance, our best attempt at using kinematics to reconstruct what is an electron pion likelihood. And we think that for a fixed total photon energy, so the 2-photon system, the only thing that can really matter is the opening angle and that asymmetry. You could also couch this in terms of the invariant mass that you reconstruct. And we've been looking into that as well. And again, we see similar spread in our predictions.
So to paraphrase, the issue is that there's all sorts of detector subtleties about the response of their photomultipliers, for example, that you can't model, and you're trying to, you said this at the beginning, but I'm just trying to grasp it. And so you're trying to make a kind of empirical model of their model.
Yeah.
And then understand the statistics of that. And your analysis seems to expose that there's a huge, much more variance than they might have guessed based on kind of naive Poisson statistics.
Exactly.
It's confusing business, isn't it?
Yeah. So again, we're trying to do our best effort, our most complete effort, and this is what we're getting to.
Right, but your job is to point out to them this Achilles heel that they have to address.
Yeah.
Okay, thank you.
Yeah, thank you. So we tried to correct for this effect, deriving these noisier cuts and applying them to the more robust sample. And what we think is that this could push up that expected background by about 100 additional background events. And I didn't say this before, but the excess itself is about 560 events plus or minus 120. And so if you have an additional 100 background events, that will reduce your significance by about 1 sigma. So We think that there might be an additional 1 sigma of error budget in their analysis that should be there. Again, we're still debating with them about it.
What does that reduce the significance of the excess to?
So it goes down to somewhere in the mid 3 sigma. Yeah. So definitely doesn't vanish. So the other thing that we did in the same paper was we looked at a new scattering effect that hadn't been explored in previous background studies. So one thing that happens a lot in standard neutrino scattering at these energies in detectors of this type is collective scattering off multinucleon states, proton-proton, neutron-neutron states inside of this hydrocarbon detector. And so what we pointed out is that if this is a proton-proton state, then you could scatter off it and emit a photon, and you actually get a 2 times E squared enhancement, I guess, relative to what you might naively expect. This is a proton-proton system rather than a single proton system. And so we did this calculation. We were really hopeful about this because you'd think that this rate scales like normal neutrino scattering times alpha EM, maybe times 4. And the anomaly is a probability at the level of a few times 10 to the minus 3. And so our naive counting was that, hey, this might be actually comparable to that. As it turns out, the answer is maybe not quite. So we think that events of this class, they have the perfect shape in this energy spectrum to look like the excess, but the total predicted rate is on the order of 41 events. And so sure, this could contribute to some of that 500, but it's definitely not all of it. So maybe this could check off another half sigma if you're counting significance of the anomaly. So when we put all the effects that I talked about together, our updated estimate of this red background and this 2p2h gamma one, this is our expected updated version of the plot that they use that show their expected background is this solid black histogram now. The systematic uncertainty on these is what's shown as the hatched part, and then data is where it was before. So we're not updating what their data look like, we're just updating what we think the background should be. And the shift from their predicted background is this dot dashed line going up to those solid lines. So we think the backgrounds should be shifted up significantly that lead to an updated significance on the order of 3 sigma. Definitely not enough to put this to bed, but maybe not enough to be as hyped about the MiniBooNE anomaly as you were an hour ago. I'm sure you all walked in very excited. So let me just end on a positive note. I put a bit of a wet blanket on a lot of these results over the last hour, putting scrutiny on them. All this is to say, I still think that the future of these neutrino experiments, especially these Earth-based ones, is really bright. I think one key thing that people have started tuning into over the last few years is using these facilities, especially these really rich detectors with this great particle ID, using them effectively as proton beam facilities. And so one class of models that you could look for in these facilities is long-lived particles. So these neutrino beams work under the principle of hitting protons on a target, focusing the charged mesons in the forward direction or opposite charge away, and then having a large decay volume to get rid of those charged mesons, a lot of earth to get rid of muons, and then your neutrino detectors downstream. This same principle is great for looking for long-lived particles, because long-lived particles like heavy neutral leptons or dark photons can be produced in the decays of these standard model mesons in that decay volume. And in many models in a lot of the parameter space that has yet to be explored, these new mediator particles would have lifetimes on the order of the distance between where they're produced and these neutrino detectors. And so they could decay inside the neutrino detectors. And often the channels that these long-lived particles would decay into are signatures that are very difficult for neutrino scattering backgrounds to fake. For instance, a muon and a pion with a certain invariant mass, or a dielectron signal with a certain predicted opening angle, those types of things. There's also, I can talk about this offline, but for the upcoming planned DUNE experiment, the hope is to have not only a liquid argon detector in this near detector site, but also a gaseous argon one. And they'll have even better particle ID, even lower backgrounds than the liquid argon. And so I have a way incomplete list of references, and again, I'm happy to discuss this with anyone who's interested, but some things that people have started exploring are these different classes of long-lived particle models, heavy neutral leptons, axions, axion-like particles, you name it. That these upcoming detectors, this is DUNE in this case, can really blow the water out from what's been done before, looking for these rare striking signals, hopefully looking for some PSM physics. So all of this is to say, I hope I don't leave you disappointed thinking that there's nothing new under the sun. I think there's a lot that we still can do and will do in the next decade or so, and hopefully we'll discover something. So I'll leave it at that and just say that these long-standing anomalies are very rich and interesting, but even detailed scrutiny of them leaves some work to be done. I think that single pion background is something that we all need to be paying more attention to. I wouldn't be surprised if these other experiments start to measure their single pion rate at these low energies and see something that's consistent with their predictions. And MicroBooNE has started to test this oscillation hypothesis pretty stringently as well. But nevertheless, I think there's still hope to be had. I think that we can do a lot of good work in the coming years, and hopefully you'll stay tuned for future discoveries. So I'm happy to take any more questions and keep chatting. Thank you. Yeah.
I just had a question also about, so I got confused, and I don't know if this was already stated, but did MiniBooNE send you their simulated data as well as their data?
They sent us some amount of simulated data. Oops. So for instance, this histogram here was produced from some of their simulations, but not to the level that we could like reconstruct their likelihood function, for instance.
And were you also able to simulate or try to resimulate what they came up with the simulated data, or is that something?
No, because this is all like at the end of their analysis chain. This is a bunch of observables that they would expect about these events, and it doesn't include all those like detector effects or the other effects upstream. And so I don't think we'd be able to go backwards in any sensible way.
Did you understand why your 2-proton scattering rate was lower than you would naively expect?
I think we were being too naive when we originally thought about the overall rate. So it's more than just alpha. There's an additional particle in the final state, so that'll suppress you a little bit. There is a form factor of basically how hard is it for a Z boson to find a proton-proton pair. That's like an order 0.1 number. Like these effects start to add up and give you, maybe 10% of what you would hope for. Life.
Any more questions for Kevin?
I have a question.
Yes.
You may have said, and I apologize, it's somehow a lot to assemble. It's very, very nice. Could you show us their idea of what the neutrino energy spectrum is?
Yeah.
Or,
Here you go, this one.
no, not the, I'm saying what they think their neutrino beam is like.
Oh, I'm sorry, I don't have that in here.
Well, just maybe you can just say in words or sketch it.
Yeah, so it's a flux made from pion decay, so it's predominantly nu mu's. They can focus away.
That's what sorry, I didn't mean, I meant the spectrum of the neutrinos.
Yeah, so it's
Depends
mostly
on the energy spectrum of the pions, obviously. I'm guessing it's peaked at like 10 GeV, or where is it?
No, it's lower than that. The neutrino spectrum is peaked around like 800 MeV. The beam itself for MiniBooNE was only 8 GeV protons.
But then you're talking about an energy deposit. You're saying the beam energy is only 800 MeV.
That's like the mean energy. There's some spread to that.
So according to this plot you're showing us,
Mm-hmm.
the energy deposit is near 100% of the beam energy, or else you're just picking up the really, right? You would have thought that I would have thought that a pion that got produced would be really, I'm just trying to get my head around this situation where you collide a proton, and that's why you're thinking of excitation, because right, the excitation spectrum is not well known at all.
That's true.
All the different resonances, like the delta and the this and the that. But maybe with such low energy neutrinos, you don't excite that.
Yeah, I will say that there's flux going up to the few GeV range, and because the neutrino scattering cross-section grows with energy, that's why you're able to still have events up to those energies. But again, yeah, the bulk of them are at lower energies.
Very interesting.
Right. That's thank you.